The next reaction that we're going to do with alkenes is hydroboration oxidation. And hydroboration oxidation is an important reaction because, as we've talked about before, organic chemists want to control everything. And so right now, we already know how to make the more substituted alcohol from an alkene just with acid and water. But what we'd like to be able to do is also be able to make the less substituted alcohol from an alkene. And to do that, we'll use hydroboration oxidation. So it's a two-step process. The first one is we react our alkene with borane. Should be able to draw a Lewis structure of borane. Boron has 3 electrons, which means it makes 3 bonds. And that makes this a Lewis acid. You can ask your normal question, who has electrons, who wants them? Remember, the alkenes always react, they have electrons, or they're nucleophiles. So they're going to react with something else that wants electrons, or an electrophile, which is the same thing as a Lewis acid. This mechanism is slightly different though, because as the electron pair comes out to form a bond with boron, the boron actually donates back a hydrogen at the same time to make an alkyl borane compound. So as is the case with a lot of these reactions, we have a choice to make as far as where we put our BH2. One side gets a BH2 and the other side gets a hydrogen. So those are our two choices. So either the BH2 goes to the more substituted, or it goes to the less substituted place. And now this is a concerted process, so there is no carbocation that forms. The more substituted carbons were favored with carbocations, but now, since there's no carbocation, it really comes down to sterics. Do we want our larger group coming into the middle of the molecule, or the more substituted carbon, or do we want our larger group coming to the less substituted carbon? And it's going to be here, the less substituted carbon. Now the second part of this mechanism is not very well understood exactly how it works, but it's hydrogen peroxide and hydroxide. Hydrogen peroxide and hydroxide, and what that does is that oxidizes off the BH2, replacing it with an OH. And because the BH2 favored the less substituted position, our OH also favors the less substituted position. So we make what we call an anti-Markovnikov product. Or anti-Markovnikov alcohol. We can also do hydroboration oxidation of an alkyne. So if I take my alkyne and treat it with borane, I get the same sort of thing happening. So I can look at a transition state. Where my BH2 is adding to my alkyne. On one end and my H on the other. And then I can oxidize that off, again with H2O2, hydrogen peroxide, and hydroxide. And that replaces the BH2 with an alcohol. However, once again, this is an enol, so it's going to tautomerize. This electron pair comes out and grabs the proton. The electron pair from this bond comes to form a carbonyl, a carbon-oxygen double bond. To make the aldehyde. So even though this is an aldehyde and an enol, we still call it a keto-enol And just with the other hydration of alkynes, we found out that it stops after one addition. Unlike the rest of the alkyne reactions that usually add twice, the hydrations, because they form enols which tautomerize to ketones and aldehydes, stop after one addition. Now there's one additional reaction that alkynes will do that alkenes don't do, and that is that terminal alkynes are reasonably acidic. And the pKa is about 25. So it's much more acidic than a normal CH. So if we treat that with a strong base, something like sodium amide, so NH2 minus is the conjugate base of NH3, and ammonia has a pKa of about 38. So NaNH2 is a good one. Another one would be sodium hydride. Hydride is the conjugate base of H2, which has a pKa of about 35. So either of those are strong enough bases to deprotonate this. So what happens is we form this anion. We call this an acetylide ion, which now we can react with something else. And one of the things that we can react it with is an alkyl halide. So if we do that, here's my nucleophile. My nucleophile can come in. Here's my leaving group. I can do an SN2 because this is a methyl halide. And here I had 1, 2, 3 carbons, and now I have 1, 2, 3, 4 carbons. So I can use this reaction to lengthen my carbon chain. And you can really use that reaction anywhere that you have a nucleophile. So for example, you have an epoxide that you treat with an acetylide ion, and that would just ring open my epoxide. Here's my nucleophile. There's my leaving group as the bond to oxygen. Here's my O minus. So the stereochemistry of this has to be going opposite of where the epoxide was. Then the last thing is I just need to reprotonate my O minus with water. And I can add a triple bond to my ring.